Greetings, Gen Chem students. I'm going to create some online video demonstrations related to that scientific revolution that occurred in the early part of the 20th century. And that revolution was a direct result of the discovery of the quantum mechanical nature of the physical world. And that discovery, that revolution, completely changed our understanding of how the physical world is structured and how it operates, how the physical world operates at its smallest, most fundamental level, at the level of atoms and molecules, those little tiny bits and pieces from which all of matter, everything in the physical world is composed. And you know, from watching the first 4 Show Me videos related to the quantum mechanical revolution that are posted on D2L. The first 4, there are 18 of those videos, but the first 4 introduce this quantum mechanical revolution. You know from watching that some of the revolutionary ideas that came out early on with respect to this new physics include the following. 1. Energy, E, is equal to N times H times nu, where N is a counting number, a whole number, 1, 2, 3, 4, 5, etc. And H is Planck's constant, and nu is the frequency of radiation. And this is telling us that energy is quantized. And that means energy comes in whole number units, little packets of very discrete size, of size H nu. H nu, Planck's constant times the frequency, is literally a packet, a particle of energy. So this revelation, which was introduced by Max Planck back in 1900, shows that energy, like matter, is particle-like. And that was completely unexpected. But anyway, you have that. Shortly after the discovery that energy is particle-like, along comes Albert Einstein. And it was well known for hundreds of years, for centuries, that light travels through space as a wave, that it's a wave-like phenomenon, right? The fact that light bends around corners, light diffracts, light refracts, light creates rainbows, all of those things are wave-like properties, indicating that light is a wave. However, Einstein showed in 1905 conclusively that yes, light travels through space as a wave, but when it interacts with matter, it does so in a particle-like way. And he said that the energy of these particles of light is equal to H times nu, where H again is Planck's constant, and nu again is the frequency of the radiation. And what this indicates is that light is both wave and particle. And we have the wave-particle duality of nature, and that is bizarre. This was a difficult pill to swallow for scientists around 1900 because in that old physics, everything in the macroscopic human scale world is either a wave or a particle. It can't be both because they're mutually exclusive ideas. A particle is something that has a unique position in space, whereas a wave is something that is spread out, smeared out. So how can something be both particle-like, localized in position, and wave-like, smeared out? It doesn't make sense in our human scale world, but it appears that at the level of the small level, the level of the tiny, the level of atoms and molecules and light particles, that indeed light behaves as both wave and particle. It has this wave-particle duality. That is strange, but it gets even more strange. Shortly after that comes along, this was Einstein. This is what he got his Nobel Prize for indicating or discovering that light has this particle-like property, that it's a particle wave phenomenon. But then after that comes de Broglie, shortly after Einstein, and de Broglie shows that not only does light behave or have this wave-particle duality, all of matter does as well, because de Broglie was able to show that matter has wave-like behavior. Now, it's known that matter comes as particles, but de Broglie showed that it also has wave-like behavior, and that's shown in de Broglie's equation. And we talked about this in the videos. Lambda here is the wavelength, and h is Planck's constant. M would be the mass of a particle, and v would be the speed or the velocity of the particle. And what this revolutionary equation shows is that anything that has mass, which is a particle-like property must have, and is moving, must have a wavelength, which is a wave-like property. So wave and particle-like behavior are combined together. And now it's shown that matter is wave-like. Even you have a wavelength. You have a matter, you have a mass, you move, therefore you're going to have a wavelength, a lambda. But because this Planck's constant is so incredibly, ridiculously small, that wavelength, when divided through, or when h divided through by our huge mass, makes the wavelength unobservable, immeasurable. But at the atomic level, that wavelength is massive, or is significant, I should say. So wave-particle duality extends to everything, matter and light and energy. And now, the last thing that we want to discuss tonight with this video is that the next big discovery was that the energy of atoms is quantized. So these, through experiments, it was revealed that atoms can only exist in very specific energy states, not just any and all energies, but only very specific discrete energies. And that's what we're going to be demonstrating with these online video demonstrations tonight. So you have this video that I gave you a link to, and the protocol that goes with the spectroscopy lab. Now there are 2 other videos that follow that you need to watch, but this is the end of this video. The introduction to these demonstrations of the quantum mechanical nature or spectroscopy. Let me stop this guy.